Well, thank you very much, Thomas, for this this introduction that put on the table very well the ALICE objectives and main developments at the level of landscape. I will share my screen. Okay, because we are going to start talking about the habitat mapping, as Thomas explained, going from in situ data to large scale. And in this consecutive content of words of this workshop, on which we mentioned landscape, habitats, ecosystem service, and connectivity. Better said, landscape, habitats, connectivity, and ecosystem service mapping that are not something that is widespread in the middle of nowhere, but it's something related in the concept of ALICE towards the final development of the blue and green infrastructure network schemes that we aim within the project. When I am going to tell you a storyline. On which I am going to explain how we use the information for going from in situ data to geographical scales when creating habitat maps. But I will stop 4 times or a number of times to demonstrate you with hands-on exercises with some colleagues that are expert in the topics that they are going to explain you, that are very like the key steps within the whole process. When we talk about spatial information at the landscape level, it's mandatory at least in the context of Europe to talk about Copernicus program. So the different services of the Copernicus program allow us accessing information about marine, atmospheric, climate change, and so on information. But here we're going to just focus on the land and the Korean land monitoring service that provides us with a large number of services and data and methods that can allow going for specific targets in our projects with very detailed information about different issues. We have within the different approaches of the Korean land monitoring service, since from the pan-European scale to the local scale, we have information about riparian zones, the urban atlas, about detailed information of the coast areas. It's a new project that they started some months ago. Nature 2000, we have the high resolution layers with very valuable information. And we have, following the EAGLE scheme, the Korean Land Cover Plus project that will give us briefly the different instances that give us information, advanced information in the way that we are used to manage the Korean project, the Korean land cover. And so we need, when talking about habitats, we need this spatial data. And we know that spatial data is not static. That spatial data changes through time, going from past landscapes that we had decades ago, and the drivers, natural and anthropic drivers, changed the landscapes towards what we have now. So we need also not only spatial data, but we need the knowledge about temporal dynamics. This available information that comes from Copernicus or comes from previous projects that are easily available sometimes is not enough for fulfilling our objectives when we work with the distribution of biodiversity, the distribution of vegetation, because they are usually created following vectorial approaches that inform us about static thematic maps that has not the enough thematic resolution that we need, the spatial resolution, the temporal resolution, we cannot update easily. So sometimes, as Thomas explained, we can also take the decision of work directly with our with the satellite information, making a classification of the satellite imageries. So in this case, as Thomas explained, we can work at the pixel level that can afterwards translate into patches, but we can deal with the dynamics of our territory following our classification schemes, defining our own typologies, and using all the powerful of remote sensing, combining satellite and other sources as old aerial photographs, LiDAR, radar, for creating our maps. In this case, we can use the information we have through time, the remote sensing information, for assessing, once we have defined a region, assessing the changes between and or among our land cover types, and making relationships of what occur, for example, when burning shrublands or burning certain land covers, and how vegetation recover afterwards. Of course, we can make an spatially explicit representation of that changes that give us a knowledge about how landscapes evolve. But again, we go to complex territories as occur here in the Mediterranean or the European domain. We have very complex territories, very complex land cover patterns from the top of the mountains to the coastlines. That, when talking again with the distribution of vegetation, we're talking about biodiversity, or we're talking about the topic of this presentation about the habitat maps, we have to go in more detail with our in situ data, with our expert criteria for getting our final maps, for afterwards working with our conclusions and application to land management as occur in ALICE, when we aim developing the blue and green infrastructure schemes that improve the landscape, the landscape functioning and ecosystem services. A good example is the management of information for reporting following the Article 17, the Nature 2000 areas under the Habitat directives. So we need go much more beyond of landscape dynamics, of how landscape change. We have to go into the distribution of vegetation following the scheme of the Annex 1, and the distribution of the habitat types following the scheme of the Annex 1, and not only talking about the distribution, but also about the conservation status, also about how the structure, functioning, the vulnerability that affect that habitat types changes, for finally defining the management plan, local actions for improving the distribution and ecological status of that habitat types. We can face that problem at the regional level, at the local level, more or less, but afterwards we have to extrapolate to whole geographical distributions, to biogeographical distributions. For example, we faced in a project that we developed a couple of years ago in Turkey, on where we have to go in an area that is more or less half of the Iberian Peninsula. And going into the ALICE project, as Thomas told us, we have 4 case studies that on which, even though they are more or less regional scale approaches, not as big as I explained you in this example of Turkey, we have distributed throughout the Atlantic region. And there is a very important thing. We need methods, we need data that is comparable in space. We need to compare the different case studies because we want to understand how drivers of change affect the landscape dynamics, affects the biodiversity distribution. And we need methods that can be repeated continuously, or having a periodicity in time for assessing how the changes affect the distribution of landscape features and affect finally the ecosystem services. During the workshop, I will focus mainly on the Spanish case study. This is an area located in the north, in the region of Cantabria, the eastern part, sorry, of the region of Cantabria, for demonstration you in the hands-on how everything that I am going to tell you theoretically with some examples can be done, or is done actually with the programming and GIS methods. So for fixing 3 main steps that we are going to explain during the presentation, we are going to talk about how we use information for creating habitat maps. So we want first to map vegetation patterns. Once we know the distribution of that biodiversity, the distribution of that habitats, we need also to understand how the different parameters about the structure of that vegetation, how vegetation functioning changes. So which are the drivers, the processes that manage that patterns, for creating a dynamic of the system, and finally how that dynamic affects the functioning. For once understood, defining reporting and management actions that allow us using that well-established monitoring, creating restoration and conservation actions that preserve biodiversity while improve ecosystem services as the project Alice aims. So yes, firstly, focusing on the habitat mapping issue, as I told you, sometimes we're talking about the distribution of vegetation. We cannot use directly really available maps that we can download from somewhere. I talked about Copernicus, but we also can talk about any other development of any project, because we need creating our own schemes, our own analysis. We have our own objectives, and we need to start from in situ data, from expert criteria that can inform us about what we need, but specifically for certain points in space. So here comes the use of remote sensing as a very useful tool with the capability of enlarging our observations from in situ data in a cost-effective manner. But this needs to make some methodological steps that we will try to show you today in this first part of the workshop. This method of remote sensing is not different from the traditional mapping system. In fact, they are complementary tools that need to be put in common. So Copernicus and remote sensing and modeling should not be understood as something that replaces, should be understood as something that improves. So we have our in situ data, and that's what we have. We can photo interpret, we can go more to the field, but we will keep always that. Remote sensing arrives to the mapping, to the habitat mapping world science for improving, for allowing the enlargement in a cost-effective manner of that observations that we make, like experts, like botanists, and so on in the field. So they are not something that excludes. It's something that need to be complemented with the traditional, let's say, traditional expert-based mapping system. And the powerful of this, I'm going to explain this, and Anna afterwards will tell us something more about remote sensing. But I would like, hopefully, to spend 1 week talking about Copernicus and remote sensing, but that's not the objective of this talk. But everything is based on the capability of remote sensing, as much as you should know, of watching beyond what we can see with our eyes. So by using the electromagnetic spectrum capabilities within the different bands of the satellites to interpret what do we have through the different spectral signatures of each land cover, of each vegetation type, of each ecological status, have on the reflectances of the responses of the ground with the interaction of the energy that comes from the sun. So these allow us creating the spectral signatures, as Anna will spend a little bit in a while, for working with the data for defining the different land cover types. So once we arrive to this point after this theoretical explanation, we have to start think about what actually matters when creating our habitat maps. So we have information, and we have other information that we don't have, and we have data and methods that we can manage, and we have other things that we will have not still for the moment at hand, so we cannot do everything that we want, but we can do quite a lot of things. So we have to start thinking in a SWOT manner to be able to define the best we can do with our data. So in trying to simplify the approach for habitat mapping, we created these 4 boxes that try to conceptualize, and are the 4 boxes on which we will have some hands-on exercises that will allow you to see how things can be done, for afterwards try to repeat by yourselves with our case studies, with your own data, to repeat the things that we are going to explain you. How we decided not to develop this workshop like exercises on which we step by step all together repeat what we are going to tell you, because we are quite a lot of people. We are almost 200 people, registered at least. So we prefer to show you, but you will have a demonstration databases of all ALICE case studies that you can download or playing with. And of course, the most important thing is that you will have everything explained step by step that we are going to show you now, for allowing afterwards you to repeat in your at home, working with your own time and methods. So, well, we are going to explain you theoretically each of these 4 boxes, and afterwards, within each of the boxes, you will have a hands-on demonstrative exercise. So, for doing our best, so for answering what actually matters, for habitat mapping, we have to define first a classification system. So we need to know what do we want to map. We need to know what do we want to look for when we go to the field. We want to map only forest. We want to map only deciduous versus broadleaf forest. We want to go into detail with the dominant species, with the different genus, Fagus, Quercus, and so on. Or we want to go also within the subclassification of each forest type. Or we want to go into the different conservation status or structural developments of each subclassification of forest community. So we need to define first a classification system for afterwards define the level of that classification system for mapping our patterns. Then we need occurrence data of what we want to model, what we want to map. We define first the classification system, and then we need occurrence data, in situ data for that thing that we want to map, for training, for validation, our models, our modelizations. Then we need predictor layers. We need information for extrapolating, as I explained you with talking about remote sensing, for extrapolating that observations. And finally, we have to put in common everything with a modeling procedure that will give us an outcome that we'll have to manage afterwards with post-processing analysis, mainly in a GIS environment, for creating our final maps that will allow defining the management actions, making the reporting, and so on. Starting with the classification system, we have many options. I told you before about Nature 2000 reporting following the Article 17 and so on. So we have there the Annex 1 that defines a number of habitats, a number of, let's say, boxes of habitats, because they have not an ecosystem-based approach. They are boxes of things that we have to report, we have to talk about. But for going into detail within that boxes, we, for example, in our work within the Nature 2000 and with our ecosystem monitoring world, we use EUNIS classification that allow the experts to define some typologies that can be tracked and can be modeled afterwards, and that follows the list of the Spanish habitats defined from the ministry. This is a hierarchical classification system that can be or should be managed, handled following expert criteria for getting finally homogeneous classification of vegetation, of biodiversity, that will explain much better than me Borja Jimenez Alfaro from the University of Oviedo and the biodiversity mixed unit from the University of Alvarez of Spain, and he's a botanist and very expert person in EUNIS and everything that relates to vegetation. So I stop here my presentation and I leave Borja to start talking about this.
So hello everyone. Very nice to be here in this winter school, and I will continue with explanation about habitat typologies and training data. I would like to start with a report that the European Environmental Agency made a few years ago. And basically what they wanted to do is like to translate all the effort that has been made in vegetation mapping in Europe in the last years to try to see how all this information can be used for habitat mapping. Because you know that probably many of you in Europe, we have nature conservation targets, which are the European Habitat Directive habitats. But the problem is that in most cases, habitat mapping has been based on vegetation units at different scales and in different regions. So basically, the main aim of this report was to detect how in the future, in Europe at least, we can get better maps that are useful for different purposes, and mainly nature monitoring and habitat mapping. So here you can see a few items about what were the challenges that were that point out in this review. And basically the main point is that we really need to have better maps based on GPS data and based on remote sensing data, so the resulting maps we have can be replicable in the time, and they are much more useful. And this is not exactly the same approach that traditional vegetation mapping has used in the past. So our challenge is to find a way that using some kind of vegetation background, or let's say botanical information, we can define a series of habitat types that then we can model and we can spatially put in a map. So the first question that we have in mind is what to map. What are the real scale of the habitat units we have to use? And in this graph, you see that in general there is a close relationship between the scale of your area and the vegetation unit. I mean the grain of the habitat or vegetation unit that you want to map. So basically, if you are working a very narrow scale, you can map individuals of plants, for example. And if you are in a very large region, typically what you are really mapping, you probably will be like large vegetation units or formations, or maybe you can get some land cover map. But if we want to make the mapping applicable for conservation planning, we need to somehow rely on the good ecosystem types or habitat types that we are concerned about in nature conservation. And so we are somehow like between a vegetation type or a community, because we would like to differentiate different forests, because we know they are functionally different, but we know they are also different in species composition, but we cannot go to the details of all single species. So that means that what we really need is to make large scale maps, or let's say regional scaled maps, and to use a vegetation unit or habitat unit that are like, let's say, close to a vegetation type resolution. And this is the main challenge that, according to this graph, is here in this red cycle, because it's, let's say, a gap. So if to deal with that, we need a classification scheme. And I don't know if you are aware that currently there is a global classification of ecosystem types. This is a project founded by Australian colleagues and the IUCN, and they are now producing a global list of ecosystem types that can be comparable across different continents. Something like deciduous temperate forest, for example. Yeah. So the main idea is that, under this classification, this provides you some kind of ecosystem types, and that you can compare across different countries, but then you need to go a bit in detail in your region to see how your habitat units match with that. So we have something very similar in Europe, and probably you know about this. This is the EUNIS classification. So is the European Information Nature System, and they basically, in the website, this is what you can see here on the right, you can have two, let's say, habitat typologies. First, you have the EUNIS classification system, that is really a classification of habitats, and then you also have the Natura 2000 habitat units. And it is important to remark that the real classification of habitats in Europe is the EUNIS classification typologies, and not the habitat directive habitats, because they are just a legal instrument. So we are going to map what we need to focus on in Europe is this EUNIS general classification. So I will give you an example. This EUNIS classification is a hierarchical system. So let's say you want to define a unit for a forest. We have something that is called first EUNIS level, number G, and is defined as woodland, forest, and other woodland. Then we go to the second level, G1 is broad-leaved deciduous woodland, and the third level is, for example, the beech forest of Fagus woodland. And then you can go to the fourth level to find exactly you have something regional, okay? What we found years ago is that at the continental level in Europe, this third level of EUNIS classification is quite okay. It's something like more structural, functional, and at the regional level it's probably not enough to make mapping, but it's good to make comparisons across different countries in Europe. So if you go to the website of EUNIS, you also probably will find that there is something called a revised version. This is something that is now going on, and basically the idea was to refine this third level of classification to find something more ecologically understandable, okay? But for the moment, this is not complete. It's just to let you know that it is now happening. But I will continue with this 3 and 4th level classification of units to let you understand what are we doing now. So I will do it by 3 case studies. The first one is the mapping of habitat types that we did with Jose and with the IH Institute in Cantabria region in Spain. So basically what we wanted here is to have a relatively quick habitat mapping of Natura 2000 sites. And we used a combination of new field work to collect GPS locations of different habitat types, and also we used traditional vegetation maps from which we collected maps corresponding to our units. The most important point here is that we focused on both UNIS and Natura 2000 habitats. So our target was to map Natura 2000, but what we found is that for doing that, what you need to map first is the UNIS classification. Why? Because with UNIS classification habitat, you have the broad range of habitat types. Some of them are protected and they are part of the Natura 2000 protected habitats, but some of them are not. But if you want a comprehensive habitat mapping, you need to use all units of vegetation or habitat types available in your study region. That's why we are focusing on the units types. So we made some kind of methodology to proceed with these maps based on remote sensing. And even if we focused on the Natura 2000 units that you see here in the table, that's when we realized that for getting this resolution, what we needed really is to map the UNIS classification habitat types first. Is what I will explain you now in a different example. This is our case study 2 is for Central Anatolia, Turkey. This was a project for developing a Natura 2000 system in Turkey, and the project wanted to make an example of new habitat mapping in Central Anatolia. That means approximately 1/3 of Turkey, so it's a huge area. And we needed to make a map from scratch. So basically, we didn't have any basic vegetation map or something. And at the beginning, the project wanted to make some kind of traditional mapping, like go to the field and use orthophotos or some aerial image to digitalize in the field and to involve a lot of people in the process. But we did some calculations, and using a traditional mapping, this would cost approximately 100 million euros, and you would need more than 5,000 field workers to do it. So it was something that had no sense, and we decided to go to a more practical view. So we based on field data, which means that we made some kind of training for local experts and botanists. In total, there were 22 field workers. And what we made, it was a systematic field survey over natural areas. And we defined natural areas using the land cover 2012. So that means we defined broad units like forest or open grasslands. And we asked the field workers to make transects by car, just crossing these areas and then collecting GPS points from these areas. So in 2 years, we were able to get 60,000 GPS points and almost 200,000 map points. That means something that is not really the location of the field worker, but it's something that you can interpret in the landscape. So the main point here is that in 2 years, we were able to collect a lot of field data that then was used for habitat modeling using the remote sensing and topoclimatic variables. But the critical key point here was to define the units to map in the field. So here is when we adapted for the first time this UNIS classification to our region. So our region was Central Anatolia. We started working at the UNIS third level of classification. That means, for example, E12, this is the third level, which is quite common for all Europe. But then we defined the fourth level, which is something adapted to our region. This case was Central Anatolia. So we defined, for example, different types of steppes or different types of woodlands, which are only occurring in Central Anatolia. So that means that this fourth level is unique to our region, but still the third level is comparable with other, in this case, oak woodlands from all of Europe. And we have here the list of all our points. And with this data and using remote sensing variables and the modeling framework that Jose will explain you in the session today, we were able to produce a general map. This is a map of major habitat units in Turkey. The good thing of these maps, here is a multi-classifier map, so it's like some visualization of a traditional map, but you can also map just one single unit, for example. So the main point is that any single of these habitat units can be correlated to a Natura 2000 unit because we have the match between both systems. That means that if we are going to make a complete habitat mapping, we need to use something like UNIS classification types, but then we can always link these units to the Natura 2000 types that are under protection. Some of them are, but some others are not. So just to finish, the case study number 3 is the mapping that we are developing for the Atlantic region in the northwest part of Spain, and part of it is also one of the targets of the ALICE, this ALICE Interreg project. And here, basically, what we are doing is to try to calibrate all these methods and to try to find the best habitat typology that we can use for making automatic mapping of habitat types. And everything is explained here in this slide. This is our study area. You see this blue color is the Atlantic Spanish region in the northwest of Spain. So we consider this is like our biogeographical region. And basically what we did is to adapt this UNIS hierarchical classification to a level 4. But this is not the level 4 that you can see in the website of UNIS. This is the level 4 that we adapted to our region. That means this Spanish Atlantic region. So basically, we adapted the UNIS classification system to our particular region, developing this fourth level of classification. Sometimes the units we are dealing with are 100% the same of the number 3 you can find in another region. But in other cases, we had to adapt exactly to the ecological properties of these units in our studied region. This is a way to optimize the habitat mapping and modeling. You can see here that some of these units of EUNIS are linked to a habitat directive, to the code that is under protection in Europe, but others are not. We have like some acidic fens here, for example, or we have some forests that are not in this list that are forests that are existing in the wild, but they are not protected. But we need to map them anyway. We want to make a good habitat mapping. And you can see also that some of these units corresponding mostly to wetlands, for example, or small habitat types that have very low scale resolution, that they cannot be modeled because simply it is not possible to make a model based on remote systems. So another important point is that all these units we link with GIS here means that they are relatively dominant in the landscape and they can model using remote sensing and field sampling, but not all of them, okay? So this is also something important when you want to report the trends of habitat types for Natura 2000, for example. You can approach many of the habitats using habitat mapping and modeling in this way, but some others would need additional fieldwork and additional, let's say, complementary studies. But in any case, most of forests and grasslands and shrublands and major dominant units in the landscape can be modeled. So at the very end, what we have mostly is a field sampling that we are conducting almost every year. So every year we have some botanists in the field that are collecting GPS points corresponding to this classification system. And sometimes we need very good data. We can also go to small vegetation maps made, for example, in national parks or natural areas, and we can collect additional data points from there if they have been done in very big detail. And we mix all these field information and we make some standardization. That means to put all GPS points or all locations under the same habitat typology. You need to conduct some spatial filtering to clean up the data, to reduce the spatial autocorrelation. And at the end, what we have is a set of occurrence data, like locations, accurate locations, which will be our occurrence data for the next step, which is modeling. And it is important to remark that this occurrence data is optimized for our studied region and optimized for being interpretable in terms of both the EUNIS habitat classification at level 3 and the habitat directive typologies. That means that the final maps that we will get with these occurrence data after modeling could be used in very different ways. So you can use just for reporting ecosystem services of the landscape, or you can use for selecting protected habitats under the Natura 2000 context. And so this occurrence data is what you will have for the study case of Alice in Cantabria, is the one that will be used for modeling in the next steps. So I have ended here. I think that any potential question should be recovered at the end of the whole presentation. So I give back the microphone to Jose. Thank you.
Well, thank you. Thank you very much, Borja. So we have heard a very good explanation of what I wanted to tell you about. We need mapping something that we know we want to map, and something that we can interpret and find in the field and translate into our occurrence data. So once we have defined, as Borja perfectly explained, our classification system, and we use EUNIS for different reasons, as Borja explained, we need occurrence data. We need something that puts on the table, on the GIS table, the spatialized information of that classification typologies, both in space. I mean, we need to cover the whole study area that we want to map, that we want to monitor, and also in the environmental domain. So we do not only need covering the whole area, but we need covering for each of our classification typologies the whole variation of the gradients, the main abiotic or environmental gradients that we have within our study area, for having information for training, for having information for validation, and for having information of the whole variation of conservation statuses and ecological statuses that we have within each of our classification typologies that we selected. In this case, the EUNIS types of vegetation that we selected. So when we want getting this occurrence data, the first resource is going to that Copernicus, to that previous map. Let's use core inland cover as an example. We can go for that map that are easily available and download and create some using simple GIS approaches for generating random points and so on for getting our occurrence data. But what happens is that there is a mismatch within the legends that we have in that really available maps and the legend that we need for creating our habitat mapping approaches. So this approach sometimes has a problem because there are approaches based on landscape features, as we all of us know, Corinne and similar maps, that sometimes the variability within the patches is not suitable at all. And if we go to the field, we will see that some of that locations that were mapped as, let's say, broadleaf forest, maybe are not. The whole patch is not a broadleaf forest. And even though we have not the typology depth enough, we also have not the spatial accuracy enough for dealing with the habitat mapping approaches. So using this map anyway, we can get a large collection of in situ, let's say in situ, of training data used for, useful for modeling. That maybe is not good for, is not useful for mapping, for modeling, but it's useful for some kind of calibration, for controlling that our predictions will be in line with other maps, that official maps as Corinne. In Spain, we have the CIOSE, we have the forestry map with a very highly accuracy, and it's like the most official map that talks about forestry. So we have to be in line with these maps. One step beyond, we can use more detailed maps that we create, high scales with more deep typology. Talking about EUNIS, we can create our own maps with photo interpretation, going to the field. This is an example of my PhD, on which I was like a couple of years running through the mountains of the northwest of Spain and creating detailed maps at the vegetation level, not detailed legend, but detailed enough for being sure that my points will have no uncertainty, or less uncertainty that if I use other large scale map. So with this information, we are in the middle of the good and the easy. So we have points that maybe that maps is not gathering the classification that we need, but we can just give some information easily that is more or less useful, let's say more or less. We have to use with caution for running our models. But sometimes anyway, we will find the problem that I explained you previously. We will go to our in situ data, and using different approaches, going to the field for the interpretation, or using our GIS variables, as I will explain to you later. we can identify points that are not useful anyway. We have inaccuracies because of the spatial accuracy, the typological accuracy, and so on. So the final resource is the less efficient in terms of human and monetary costs, but is the really useful for running habitat mapping approaches without collecting uncertainty since the beginning, is the going to the field and doing our sampling under expert criteria, as we did, for example, in different projects in the north in our region, included, of course, the ALICE project within the Spanish case study. So we make transects, we use the expert criteria with people that know perfectly what they are doing, talking about the vegetation, the gradients that occupy that vegetation communities, for getting a perfect sampling, as we did in Turkey. For example, as Borja explained, this project was a project with funding enough for having a large number of experts in the field. And also when collecting the information, there is another source of uncertainty. We have to take into account that we can go to the field and locate a point in a map. Then we have to translate that point into the GIS environment. And we have an uncertainty of doing that translation if we don't put a lot of attention. So we have digital tools as we use in Turkey, and all of us and most of us use when we go to the field, for having a direct translation and connection through using the cloud capabilities for creating our database with high accuracy. Not only the typological accuracy, but also the spatial accuracy when we locate our points. So with this approach, we have a very useful, very good database of information for training, for validation, and for knowing not only the distribution of the habitat types, because once the botanists go to the field, as Borja explained, they collect also information about the conservation status, about the composition, structure, function, the pressures that that communities are suffering in space, for having a very good database for running our models. In Turkey, as Borja explained, we did this with almost 220,000 points collected in the field, both at GPS position and also with a very reliable definition of what was going on in the field by the botanists. This is not real. It's not the real scenario, because it never happens to have these capabilities, but we have to focus on this, covering the whole area and covering the whole gradients, but going to the minimum of points that allow us reaching suitable maps. As Borja also explained, we are following this approach in the north of Spain, in the whole biogeographical region, that now we are more or less in the middle of a project to enlarge this to the whole north of Spain, including also the Pyrenees. So we want to do this, but we, of course, as you can see there in the green dots, we have just a small part of the whole biogeographical region with that field mapping approach, because of course we cannot cover the whole territory, or we have not done still. What we have in the middle of is the in situ data of the autonomous regions, of different projects, a lot of colleagues that we have contacted with many people already, talking about this approach of working together for making habitat maps, for making for assessing the vegetation, biodiversity distribution in the north of Spain. But we have this in the middle quality. That means that there are available maps and other projects that we can use for translate their own classifications, their own maps into our classification typologies, as Borja explained. But once we have this information, we have to work with this data for making a final database for training. And I will show you just briefly, because we have not time enough for going into detail, but at least showing you. I'm going to stop sharing this screen, and I am going to share, again okay. So I go to my GIS database, on which I'm going to try explaining you easily what do we mean when we talk about, that Borja did as well, filtering our training data. So we have points that come from the field observation of our botanists, with GPS quality, with a detailed explanation of the content of the content of that GPS point, about the distribution of vegetation, which habitat types it is, information about the conservation status. So that's okay. So we have training data that we can sorry, what? Yeah, here we can classify using the different sources. I'm going to manage this. Sorry, yeah, this one I want to remove. So this information that you can see here in different colors with dots of different colors, doesn't matter the meaning of the different colors, is information that comes from the field workers. We have been, as you can see here in the legend in the GIS, the fieldwork 2019 training from, I kept the original name, is not well structured. I mean, we have a geodatabase with this well structured, but I want to show you where the information comes from scratch. So we have information from different years, 2016, 2017, 2018 is not here, but okay, and 19, that come from the field. But we have also, as I told you, we have also information that come from maps. I will put it here with another color for being able watching it easily. Okay, we have also information that come from the maps. So this information I'm going to make a zoom here. This information is not the same from the dots of different colors, the small dots, and the information that comes from previous maps. That's the information I told you that we can collect for the whole north of Spain and maybe for the whole country and the whole Europe. Just taking information from previous maps. That maps can be better in terms of suitability, in terms of quality, in terms of accuracy, or whatever, or in terms of the similarity with the classification typology that we define. Or we can be worse. They can be better, they can be worse. We can keep the information. We can keep the location of different points that can be structured using different approaches. We have patches, so we can first generate random points, or we can use different criteria, as I will try to explain you now, using the predictor variables that will be used afterwards in the modeling. So in this case, just for making it simple, well, that doesn't matter. We have here the green points are information that comes from the maps, from previous maps, okay? And the other points come from the field. So the information that comes from the fields, is not going to be subject in the beginning to uncertainty in terms of, we believe that if a botanist, if an expert go to the field and locate a point, we believe that that information is accurate in terms of spatial location, in terms of content. But when some information comes from the map, we can do our best to locate that point using different GIS tools in the correct position, but we, in the most of the cases, don't know what happens within the patch. That's what I explained you. I showed you before in that slide on which you can see a vector, a landscape patch that is located in an area that is supposed to be covered by forest, but in a shadow slope, we see that we have no forest there. But when the photo interpreter draw that line, he or she considered that was included within the forest land cover, and we accumulate an error in the landscape patch that we will keep that error when creating points for representing that patch, okay? So what can we do here? So we can use the information from predictor variables. So we have different predictor variables. We have information about from NDVI, for example. We have information from slope. We have information about the different variables, precipitation, temperature, and we have information, I have not here, it was an error, sorry, I will put it now. We have information about about LiDAR. So the issue, I didn't include LiDAR here because we have no LiDAR in all the countries and open available information from LiDAR in all the countries in Europe, in all the case studies of ALICE, but we have it at least in Spain for the case study. So if we use the information from LiDAR, we can, I'm going to look for for the LiDAR information. Spain, environmental predictors, LiDAR. So I can do this example with all the information that we want to use, but let's go here in detail to an area on which we have information about LiDAR. Here in the legend, you can see that we have colors from black to white. That means that when the pixel is whiter, it means that we have a higher higher altitude of vegetation. If we go to the, I'm going to uncheck the NDVI. If we go to the orthophoto, we can see that in the areas on which we have forest, we have an information of LiDAR telling that the vegetation is not zero height. It's has a value of height over the ground. Okay, so in the areas on which the trees are higher, LiDAR informs us that the height of vegetation is higher. With NDVI, we can also do something because we have a value of NDVI higher when we have greener vegetation, when we have something that is not ground data. But as you can see here, if we use only NDVI, if we use only information from multispectral imagery, we cannot be sure where we have forest or where we have other thing that is vegetation, but not with tree stands. Okay, so as far as we can go with the predictor variables, better will be for assessing if our information of our training information is more or less accurate. If we have time, I would go in detail into the typologies of the different training data that we have here, but I will tell you just to imagine that we use now simple GIS tools for identify which of our training data is forest, which of our training data is shrubland, grassland, of course, labeled with the different EUNIS typologies. So if we have information of which EUNIS typology is our training data, sorry, I want to here the EUNIS, okay. This point is forest because we have a EUNIS typology is talking about a Quercus forest. So at least in the beginning, just to make a simple example of this, if we open our LiDAR information, we should have here a vegetation height that was over that has a value. I select here LiDAR. This value need to be 4 meters, 5 meters, 10 meters, 2 meters. So it's not a very mature forest type that we can check in the orthophoto. It's a forest type of around 3, 4 to 6, 7 meters that will allow us making an extraction of information that can be added to our information from the training sites. Using, if we go to our GIS, wherever you use ArcGIS, QGIS, or R, you can do a simple analysis, spatial. Here in ArcGIS, using spatial analyst, you can make an extraction of each of many raster layers. You can include as raster layers are predictors as much predictor layers as you want. Here you have in the first you have access to the material of the hands-on exercises of the workshop, and here you have some variables. In the first hands-on, you have a guide on which would you have a presentation, and you have a data folder on which you have the EUNIS I am showing you with the different codes. You have the variables that you can use in your GIS for including in this kind of analysis that will add the different information of the variables will be added to each point of the training data that you have that can be afterwards used for filtering if the points that we collected from previous maps are true or are not true, truly related to our to our EUNIS typology that define each point in the base of expert criteria. We can never have a forest or a shrubland EUNIS type if our NDVI is value 0 or value 0.1. We should not keep that point because the uncertainty will be quite high. If we have LiDAR, it's very useful for identifying areas that have a tree stand typology or not. So with this kind of information that is collected in the database of the points, we can just take that Borja, as Borja explained, we can make, sorry, I'm going to here to close this. We can, sorry, I'm going to, yeah. We can use this information for, as Borja told, and the word that he used was filtering our training data, but independently of the origin of the information, it's much better if we have in situ data, but if we have not in situ data, we can use map data for selecting random points or with more a locally tailored design strategy for selecting that point. But finally, we can filter that points with the training data for being as sure as we can that the point is really talking about the EUNIS typology that we define for each of the points. Once we filter and clear this training database, we are already I'm going to stop the presentation of the GIS thing and going to, just for being sure that you are watching the presentation. Once we do that, we have our training data, okay? We have been talking about the classification system. That classification system is transferred using different sources of information with higher reliability, with lower reliability to the occurrence data for training and for validation. We can use our predictor layers for filtering that training data and being sure, even though in reality, the botanists are 100% sure of what they are talking about. We need to be also sure that that information matches with our GIS environment. So it's important to be reliable with in situ data, but it's important to be reliable in terms of our GIS environments. So we are talking now about predictor layers. So predictor layers, as far as you know, is the information that we need to collect for extrapolating our training data, but you have also seen that it need to be used previously, but for filtering that information that we collect from somewhere, okay? So talking about predictor layers is a big world. We can spend 1 month talking about in a course only about predictor layers because we can talk about everything. So but just for making it operational and making it easy, we split the variables into groups. On the one hand, we have the environmental limiting factors. I mean, we have information about the distribution of topography and surrogates for climate, precipitation, temperatures, radiation, and everything that can allow us explain the distribution of biodiversity, of vegetation in the shape of habitat units, habitat types in this case, and soil properties. Some of the information is easily available. We can go to the web, and we can just download the information about topography or whatever. Or we can we have to prepare that information, but it's everything related to environmental limiting factors for defining something that is more or less potential in terms of where the different vegetation typologies can occur in space. But also we have the remote sensing with the multispectral imagery, multispectral because of the availability. We will talk about hyperspectral afterwards a little bit. We have information about LiDAR, about radar, and we have, of course, different, also information about the drones, flights, and so on. And that information can be used for developing indicators of the distribution of the vegetation patterns that we have identified previously in terms of accurate as possible training data. So as I explained,
just hold on. I have a question for you from the chat live. I think it would be good to make a short break as well to make this winter school more interactive. So Dimas Pereira Ubaya asking a question about, okay, if we want to make a change analysis between the moment back in time and today, can we use thematic map instead of field data to train and validate?
Yeah, if I understood the question, yes, if you want to, well, that's something that we will be answered at the end of the session about habitat mapping, actually. But we have to use our imagination and our capabilities as technicians, GIS and scientists for acknowledging which information do we have and which objectives do we have. For answering your question, if you want to track the dynamics of vegetation in the shape of habitat types, now I mean that we can go to the field and see what is going on. We can use our expert criteria for doing a sampling or for filtering the information that we have from coetaneous habitat maps. That's okay. We can go to the field and we can work and spare our time or money to do this kind of collection of training data. But if we are talking about the distribution of the habitation patterns in the shape of EUNIS habitat types 20 or 30 or 40 years ago, we have no information to do that. We can use, the best that we can do is to use our old aerial photographs for making some kind of photo interpretation, or we can use all past multispectral images, basically 40 years, 30 years ago Landsat imagery with different sensors in time and so on for making classifications. But can we map EUNIS habitat types at level 4 40 years ago? I would say not. It's quite, I mean, I don't want to say not. It's complex. I mean, you have different paths for making your assessments. That one of that options is the one that we use here in ALICE, is couple landscape dynamics that can be more accurately assessed. Landscape in the terms of, as Thomas explained, talking about the structure of structural shapes of vegetation at the landscape level, forests, shrublands, different crops, and so on. And then try to link the dynamics of landscape with the current vegetation patterns with the higher level of detail that we were able to map to track how the landscape changes, evolve, and try to link that evolution to the different biodiversity patterns. I don't know if do you think, Thomas, that that's more or less the question?
Yeah, I think it answers the question, because it is a tricky situation that trying to make some habitat maps in the past without any in situ data sets. So yep. I think you answered the question, so you can go on.
Oh, I want to mention also some the magics of the data processing that is artificial, that relates to the artificial intelligence algorithms and so on. That I don't know, with the time series of information, artificial intelligence algorithms, and putting in common, I don't know what now, that is something that is being developed nowadays. Maybe we can do much more in the past that we can imagine now. But the important thing is that we need to have imagination, but fed with technical criteria. And we have to acknowledge that we have some data, and we have to handle with that. Okay. So just going a little bit more in detail in the predictor in layers, as I explained you, there are some available information that we can just download. For example, information about topography that is easily available. We can download the tiles and mosaic and have large territories covered by detailed information. We have, of course, the Copernicus EU digital vision model with very high resolution at the European level, or we have the SRTM or other approaches at the world level. But if maybe we need more accurate data, in Spain we have 5 to 1 already 1 meter digital vision model derived from LiDAR, and we can download and develop surrogates as slope, solar radiation, and so on. That's easy. Download and we have it. Other times, talking about climate is a very big world. The information about climate with the reanalysis and Eurocortex approaches, and of course the Copernicus. But I'm going to just show you one tips, some pictures about what we can do. Sometimes we have available information that I have used during all the works I have done in my life. The climatic map of Ninjarola from CREAF. That is a very interesting map. It's at 200 meters. That maybe is quite rough resolution that need to be reinterpolated using different geostatistical techniques for smoothing the information at the pixel level that we have from remote sensing and other databases, and avoiding the crisp analysis with bigger pixels. Or we can use really available worldwide data sets as WorldClim or CHELSA analysis, from which we can download information from current climate scenarios, future scenarios to work with climate change and so on. And of course, as I explained in the beginning, we have to take a look to the Copernicus world that is amazing, the good and amount of information that we have now at hand for the European domain. And finally, talking about the abiotic predictors, we have another information that is not really available, but is necessary to have at hand when we talk about the distribution of vegetation with important variables as, for example, the pH, like texture, the percentage of sand of the topsoil, the different texture, the composition in terms of the structure of the topsoil, but other information. So this information cannot be downloaded or can be downloaded directly at the world level with different approaches as soil grids or the soil map of Wageningen University that we used. But when you analyze the information at the local level, at the patch level, the reliability and the capability of that information at the local scale, local to regional scale, is limited. So we decided in some of the projects, as we did in the Spanish case study for Alice, we decided to create our own soil properties maps, going to the field, taking information in the field, going to the lab, analyzing the information, and running digital soil mapping analysis for creating information, as I showed you previously, about the texture, about the pH, and developing different approaches for soil organic matter. That was not so easy. That we ended up with a mechanistic modeling approach that we published a couple of months ago about the distribution of soil organic matter in the topsoil. That was very useful for mapping the distribution of vegetation. So with this big amount of information, we arrive here the information from remote sensing. We have different sources, different satellite imagery that we can download and prepare and put in common with our abiotic information for running analysis, ranging from Landsat information that we can download, Sentinel information that we can order and download different approaches, as Anna will explain to you in a while. And of course, we can do this for, again, from regional areas, or as we did in Turkey, for an area that was almost half of the Iberian Peninsula, following more operational approaches that go in and click and download. That information that is downloaded is not as simple as download. It's information that need to be prepared. We have to identify clouds, shadows. We have to correct the information for creating maximum composite products that have no data information and reliable information for the whole area that we want to map and analyze. Derive spectral indicator, its spectral indices as NDVI and many other that we can derive from this image. And of course, we can play with the different resolution of the images that are available. We can work with Landsat, but we can jump into, for example, Sentinel that improves the spatial, spectral, and temporal accuracy of Landsat repository. But the good thing of Landsat is that we have information from 40 years ago, as our colleague asked in the YouTube chat. So with all that information, arrive new sources of remote sensing information as LiDAR and radar that informs us not only about the distribution of the different reflectance values in space, but also in the third dimension of altitude, how vegetation changes. This information is not available for all the Alice case studies, but you have an example in the Spanish case study on which we have this kind of information. Of course, many of these sources have temporal resolution, so we can play with information of phenology. We have information from spring, from summer, from autumn to get more reliable conclusions. And everything is related to the spectral capability, as Anna will explain, of the remote sensing imagery, and in this case of the multispectral imagery of differentiation between what we can see with your eyes in aerial photo and what the satellite, the spectral images, and remote sensing in general can see beyond our eyes. And this information can be extrapolated to the whole study area, giving different responses in the base of the different land covers, in this case, in the different EUNIS habitat types that we have in our geographical space. And now I will kill my presentation to allow Anna to talk a little bit more, some minutes, about how getting this remote sensing data download and processing. Anna, are you there? Okay, we cannot hear you, Anna.
Listen to me now?
Okay, now Anna is perfect. Thank you very much.
Okay, good. Well, I'm going to start my presentation about the the integration of remote sensing data into these process of habitat mapping. And well, basically, I mean, the objective of this particular hands-on is basically to understand what are the data products that are necessary for this habitat mapping, then to have a better sense of the practices or the rigorosity of the practices, the processing of the images in order to get the best available data, and then, well, to have a little insight of how the ESA Snap toolbox works. So basically, what we aim with this hands-on is for you to gain some knowledge about these products and the remote, the processing of the remote sensing imagery. Well, I'm not going to. I'm really going to go fast in this because I guess that everybody has more or less, after all these presentations, a good sense of why do we use satellites for this type of mapping. But basically, as just to mention very quickly, it's basically because they provide regular and consistent observation of over large areas, which otherwise, well, is not. I mean, this allows us to monitor actually that otherwise it would be a lot more costly. These imagery, it has they are consistent both in the way they are acquired, because they are sensors that they are achieving acquiring the information repeatedly in the same way. So they provide us as well like a well-structured time series, so they can allow us to go back in time and to have as Jose Manuel mentioned, to have a better sense of the phenology, and that's an important tool for the habitat mapping. Then, they provide us a large number of data products, and most of them they are for free. I mean, and they are for sure complement. I mean, they are complementary to the in situ sampling. So there are several types of optical satellites or optical sensors in different satellites, but this is a list of the ones that right now they're running, and they have free access, and we're going to focus basically on Landsat and the Sentinel-2. The first thing that you should be aware of is that there are different levels of data. So it's very important to have this clear, because in order to know what you are selecting for your modeling. So the first one is the level 0, which is the raw instrument data, and then is the data, the way it comes directly to the satellite. Then there's the level 1, which provides geolocated and calibrated data, but at the level of the sensor. Then there is the level 2, which are products derived from the previous one, the previous level, and these are both geophysical products and atmospheric corrected products as well. So they provide us the spectral signature at the surface level. Then we have the level 3, which are gridded and quality control data. And then the level 4, that they're basically model outputs. So what we get actually from our modeling would be some sort of a level 4. Okay. Well, this is a more detailed explanation of this type of data, but for you to know, it's important. You know that the less the level, the greater the skills that are needed. So basically, for a person that is, it doesn't have a wide knowledge of remote sensing, a level 2, starting with a level 2, that would be fine. I mean, it's easy and it's feasible for everybody. So one of the things that I'm going to focus on is basically the atmospheric correction for the habitat mapping. Why? Because this is a key issue in order to retrieve these at-surface reflectance. That is the one that we're going to use for the habitat mapping. So basically, satellite sensors, what they measure is top of the atmospheric gradiences. So it's the signal that they receive directly at the level of the sensor, and it's a combination of both the surface signal, but also mixed with the atmospheric conditions. And so if the atmosphere varies, your signal is going to vary independently of what's actually happening at the surface. That is the information that we want in order to retrieve our habitat mapping results. So basically, and just as an example, I would like to show you how this signal varies with the altitude. So how the atmosphere is affecting the signal that we are retrieving. So as you can see from the surface, that is the bottom, a black line from the surface up to the top of the atmosphere, and our signal is quite different and is quite perturbed. Okay. So what's the goal? Well, basically to retrieve the at-surface reflectance spectrum. And for doing that, there are different approaches, but the most complete are the ones that they use predictive transfer modeling, that they consider the atmospheric conditions, the clouds, the aerosol information at the time that the image is acquired. And there are different as well models in order to perform these habitat corrections. So the most popular are the 6 tests, iCore, ArcLight, Flash, you name it. I mean, this is an example. Pardon me. And this one is focused on the target is water, but and I know that we're dealing with vegetation, but it's just basically for you to see how do we parameterize and how we retrieve what's the input that the atmosphere has over our segment. So, for example, if we do an RGB, so like if we want to open an image and we open top of the atmosphere image, what we're going to see is that it's bluish. So our image is greatly affected by all the aerosols present in the blue and the water molecules and so on. And it is once that we have performed the atmospheric correction that we obtain the surface reflectance, so we can truly appreciate the real spectral signal. So in terms of the Landsat data, well, there are different archives to access it. There's well, Landsat is part of the USGS or the US Geological Service, and so they have different types of repositories, but the most common one is the Earth Explorer, and is the one that we're going to focus on. In order to access the data, the only thing that you have to do is to set up a free account and log in, and it's very simple, very straightforward. There's not much of it's not complicated at all. Once that we're in, later on I'm going to go through the web, but I'm just going to show you a little bit, and we'll see later on how it's done. So the only thing that we have to do is either to select the area that we are interested on, or if we know the actual satellite scene, we can put it and then select the date and the cloud cover and so on, and then we have a bunch of data sets that we can use. And actually the Earth Explorer has not only Landsat data, but also Sentinel-2. But we're focusing on the Landsat one. So we select the data, and you will see that there are two different things. One of them is, as I was mentioning, at level 1, that is this top of the atmospheric gradients, and then we have the level 2 that is under demand, and it's atmospherically corrected. So once that we have selected the missions that we're interested in, we can go through, we can add some additional criteria in order to narrow down our selection. And then it's just a matter of clicking over the results, and you will see that a bunch of images appear. And then in order to download it, there are also a bunch of possibilities. But the one that we need is the what is called Landsat Collection 2 or 1, it doesn't matter, level 1 or, well, in this case is the level 1, but we can be interested directly on the level 2. and it's the product bundle. So it's basically the overall information of at 30 meters, and all the spectral information and thermal and so on. So just to, well, just to resume, a Landsat 1 can be a level 1 of Landsat can be directly downloaded from the data archive, like Earth Explorer, and then these files can be later transformed into a surface reflectance, as I mentioned. But if we don't feel very comfortable using that option, we can go directly to Landsat 2 data and make a request, and in less than 2 days you will have all your images corrected. My suggestion is that if you're going to use, if you're interested in using different sensors like Sentinel and Sentinel-2 and Landsat, which are more or less equivalent, Landsat 8 and Sentinel-2, I wouldn't use level 2, direct level 2, because the methodology for this processing is not compatible with the Sentinel-2. Right, so in that case, you will have to download level 1 files and do the atmospheric correction, which has to be the same as the one performed for the Sentinel-2. These of Sentinel-2 as well. There are different ways to access the data, but the official one is the Copernicus Open Access Hub. And yeah, for that you have to also set up a free account and log in. It's very straightforward. Then draw the area of interest with that button, and select the data that you are interested in, because this Copernicus Open Access Hub thing is that it has Sentinel-1, 2, and 3 data. So yeah, it's you have to select the adequate one. The first thing that you will find is that you have to select the what is the period that you're interested in, for example. And it might be either the sensing period, so is the time at which the satellite passes over the area of interest, or the ingestion period, and is like the post-processing period. Normally, the most most common selection is with the sensing period. Oh yeah, and you will find as well descending or ascending, and it's the orbit. Basically, this is related to the time at which it passes. So it's daylight, or nighttime. So the descending is associated to daytime. Then you have to select the mission, Sentinel-2, and then you'll find that there are different product types. In here, you will find that there are the both level 1 and level 2. And you can, the level 2 is official. It's an official product, ESA product. So you can go directly as you as in the case of Landsat. But again, you can decide to perform your own atmospheric correction. Regarding the satellite platform, is that Sentinel-2 has there are two twin platforms. There's the Sentinel-2A and Sentinel-2B. So, I mean, they're extremely similar. I mean, they're twins, and if you want to enhance your possibilities of having more data, I wouldn't put absolutely anything in here. I will just do my selection with the product type, and that will be it. So once that you select once that the area of interest is selected, and we have decided that we will go for, well, in this case, I didn't specify if it was level 1 or level 2. We obtain all the results. So for downloaded is very, it's very simple. You have that button, and that will be all. There's something that you should know, and is that these products are very, they require a lot of hard disks because they are quite big. So yeah, to sum up, Sentinel-2, level 1B data, you can download it directly from the archive, or you can, and then later on perform the atmospheric correction, or you can go directly to level 2 data, which is fine, and it's an ESA product. So in order to visualize and process the data, ESA provided a toolbox that is specific for Sentinels, and it's the SNAP toolbox. You can download it directly from this web page. And then, well, the first thing that you will have to do is just launch your software, and you will see that there are different, depending on the version, the viewer is slightly different. So, for example, in this presentation, what you're going to see is the Mac version. But for example, now that we're going to go through the web page, or the software that is installed in this other computer, which is a Windows, is slightly different. It doesn't matter. I mean, so what we will do is just do the data opening and visualization, the atmospheric correction, which we are not exactly going. I'm just going to show you very briefly how it's done, but we are not going to perform it because it takes quite a bit of time, and it's highly demanding. And yeah, you can do it with your computers, and then we'll see the spectral indices. So, for example, this is just a snapshot of an image. It was open of the area as a Sentinel-2 image. One thing is that the snap also allows you to process Landsat data and different other sensors. And and here this is level 1. Well, the spectrum view provides us, we can see that it's not corrected because it has, the blue is very high, it's quite higher than the what it's supposed to be. But and we'll see it later on. And then, regarding the atmospheric correction, SNAP allows you to perform different type of corrections. The standard one is the send to core. that it would be a replica of the I will say of the official product. The reason why this model is installed in the software basically is because, for example, in the case of the Sentinel-2 data that is installed or archived in Earth Explorer, is only level 1 data. So if you want to perform it in exactly the same way, or to have exactly the same product, official product, as the one that is provided by ESA, you can use this Cento core. The problem with this atmospheric correction is that in hilly or mountainous regions, the performance is not great. I mean, it's okay, but it's improvable. Then there are other options like iCore, that is a module developed by a company, situ. And the interesting part of this module is that it allows us to perform the correction to perform the correction both for water and vegetation, and then there's the acolyte that is also very complete and it works perfectly fine for both vegetation and water. And then there are the spectral indices that, well, if you click on the optical part, there's the thematic land processing, vegetation radiometric indices, and there's a bunch of indices that they can be retrieved very easily. So this is an example of the NDVI. Well, I'll stop this, and I'm just going to show you this very, very briefly. I mean, this is the Earth Explorer that I mentioned before. It's very intuitive and it works fine. This is, for example, the case of the Copernicus Open Access Hub. And well, these are the atmospheric corrections things. So, for example, this is the SNAP. So I've been told that we're running a bit out of time, so I'm going to go very quickly. In order to open it is just this. Click on this, and it will be loaded. It's exactly what we have in here. Then, in order to visualize this data, there's right button, and then the RGB image window. And if you go through it, you can see, well, this is the level. Yeah, this is providing us the atmospheric signals, the spectrum signatures, atmospherically corrected and not. Okay. Apparently you're not seeing this. I don't know what's happening. Are you? Okay, well, yeah, so you're not seeing this, so everything. So well, anyway, if you have any questions, I'll be happy to answer them. Thank you.
Okay, thank you, Anna. So if you can stop sharing the screen.
Yeah, I'm trying. Hold on. Just trying, I don't know why this is not.
So Mariana, if you can stop sharing the screen of Anna.
Yeah, I'm trying. Hold on.
Mariana, maybe you are there. So well, just for linking, we would like doing an in live exercise, but just for clicking and ordering the selections and so on. I think it's more efficient to see what Anna explained us in the presentation that you have available in the material for following the same steps. So the issue is that we wanted to demonstrate that the remote sensing is not just clicking and downloading the images. We have to take into account the corrections and the post-processing, because of the ways that information of predictors that we use for filtering our training data, as I explained you before quickly in the GIS. I only wanted to show you that once we have our points, independently of the origin, we can check and validate and filter that training information before running analysis. And of course, when extrapolating using our predictor information, that information needs to be accurate as the training data. Otherwise, our information is not correct one, is not really something that reflects reality, and our predictions will be not reliable neither. So finally, once we have our classification system, occurrence data filtered from the predictor layers, we have the predictor layers for remote sensing, environmental limiting factors, we jump into the ecological modeling part. It's the very interesting one here. I mean, everything is interesting, but the modeling is the more visual one. We put the occurrence data and predictors together following different approaches. I would like having 2 hours more for explaining you. I would like starting with the graphical user interface of Maxent. Just downloading the program you have in the material. You can open the graphical user interface. I gave you as well a really detailed step on document for running analysis using the graphical user interface. And then, of course, we can run more efficient analysis using R, script, or Python languages. And of course, going into deep learning with the different approaches and softwares that allow this kind of analysis. So we just directly go into the example of our scripting with Biomob 2. That Isaac Pozo is one of colleagues of that we work together in the National Museum of Natural Sciences. Will show you how to couple these training data and predictor layers for making our predictions. Stop. And leave Isaac to tell in a minute this one example on this. So your turn, Isaac.
Okay, hello everybody. So can you hear me now?
Yeah, perfect.
Okay, so I will share my screen and let's start. So it's something that I want to tell is that I'm going to try to show you how to program live. This is really very difficult to do it in YouTube. I'm going to go as slow as I can, but this session will be recorded, and I have tried to save all the steps. But just in case if you get lost, just let me know. I will try to go as slow as possible. Before passing to the presentation, if anybody of you wants to follow me live, there's one step that you have to do it. That is basically install the package Biomod. This is our library that needs to be installed. It will load series of packages and it can take like 1 or 2 minutes. If you never have worked with spatial data before in R, I just recommend you to run this line, that it will load all the different packages that you might need. Some of them you maybe should have it. And while that is happening, I will go to the PowerPoint presentation and show you more or less tell you what I'm going to show you. But let me know if you get lost. So basically, Jose asked me to show you how to do spatial modeling. So basically, with the basics of bioclimatic modeling is just to compare what is called the geographical space and the environmental space, and to project how we have a set of species. Where is the niche modeling? So we are modeling the potential space of a species, not the real occurrence. So we say, according to our variables, to these environmental variables, this species or this habitat should be here. Otherwise, is that that the humans has decided not to do it. And for example, I can say here is a potential of a beech forest, but otherwise it's a city built there. So I will have to then remove these parts. But basically, we have the geographical space where I have the crosses where the species occurrence are. The gray is where the actual distribution is there. But then I will have the environmental space, that is the geographical variables that explain this, and with that I will just project to the upper box the potential zones where the species can be. And let me see if I can. Well, I cannot. I can point, but you can see in the site number 2 that the species is not there, but its potential there, and in the number 3 that the species is not there and its potential in the future, but it will have to move there. So, I mean, this of course is much more complicated, and this is going to be just to open the appetite on what can be done here, but it's just to show you. Just to make an example, I'm going to show you with the Atlantis acidophilus fagus forest. So it's the classical beech forest of high altitude mountains. So this type of forest only occurs occurs a lot in the Atlantic space, especially in France, England, and north of Spain. This is fagus forest accompanied with Quercus ilex in the small forest. So it's according to EUNIS is G16.2. We're going to use the environmental space using the Copernicus data that previously has been shown. And just to show you the resolution is 10 by 10 meters, so it's quite deep. Yeah, talking about the environmental variables that we're going to use 20 environmental variables, starting with this with the weird names is the Copernicus bands that correspond more or less with what we want to use, but also is DM is a digital elevation model. We got East Spain, it means the orientation to the east, and DBI for different periods, being July, April, and August, because the response will be different. And with all this, we're going to model. If you enter in modeling, and down below you have the let's say the Bible of papers in this. There's a lot of modeling methods. I'm going to use Maxen here, but just to know that there's a lot of it. This is a whole science itself. Just if you want to go in deep, I will give you later reference on this. Well, we can model things, and I think this question just appeared before. The most classical study will be to model actual and future conditions and make climate change studies. But of course, you can do crop estimation, you can do parasite expansion, you can do a lot of things. So here you have two of the type example. The left one, it will be the climate change, where new climates and disappearing climates exist, and you can see how fast this is going to happen, and if the species are able to stay or have to migrate, or we have to implement measures as translocation of a species. On the right side, you have an example with the giant Asian hornet, that, if you know, more or less is displacing the honeybees on especially in America, but it's basically it enters in the colonies and kill the queen and it decreases population. So we can see the expansion when it arrives to the east coast of the States. You have there below the paper that make it and see how it goes. So, okay, so as you see, we have a lot of mixture things. We have a lot of initial condition, a lot of models, a lot of model parameterization, and a lot of boundary condition. And on a paper of 2007, Miguel Araujo and you, well, Manu, just proposed this ensemble forecasting that is saying, okay, we're going to plus all models and get where most of the models say the truth. How we do this, there's a lot of ways of doing it. There's a lot of packages that do that. That's a lot of possibilities. For this presentation, we have chosen Biomod 2 because it's one of the most used. But there's many other. There's the paper there where we're explaining a lot of it. But just to show you a little bit, we feed the model with species distribution and environmental data. We just give single models. We just parameterize every model, and then we go to the right part. And so we do all the predictive space. We train a model and do ensemble forecasting and generate a new model. So let's go on to the hands-on. If you enter on the materials of this exercise, you have a series of folders there. The one that I want to show is the steps one. If you get lost, I have saved the R workspace in 3 parts of the script. So if you get lost, you can go directly to that part. On the script folder, obviously, is the script that I'm going to use. And on the modeling folder is where the simulation is going to run. You will have it empty now, but in the end, it's going to be filled with this. So with that, let me show you the presentation, the R. So I'm going to show R Studio. Can you confirm that this is being seen? Just in case.
Yes, it is. It's perfect.
Okay, so again, this is not, YouTube is not the first, is not the best way of showing this, but let's go. So first, if you don't have this installed, please run either one of these two. Then what we have to do is basically load the libraries needed. Not to go very in detail, but I'm going to load library biomod, a series of raster and spatial management libraries, and something like that. This is something that I do normally just to have a clean explanation, a clean version. I just clean all variables, so I don't have nothing on the right side on the variables. Then I will set the working directory. So if you have ever worked with that, I'm going to do it manually here and choose this directory, but you can do it by coding. So I will just say that I'm working here in Ali's seminar. So if I get my working directory just to, well, my computer is behind me. Okay, so if I get my working directory, just to know it, we're working there. Okay, so the process will be split into pre-processing, model processing, and studying the model. So in pre-processing, I basically have to prepare the model. So I have a save file that I can read. Oh, okay, so we start early. Hey, that was my fault. I already entered in the folder, so I can. Okay. Well, let me go to another session of R. Sorry for this is the live things where I have everything loaded. So if I just load the script, so this is the same, but basically is in my with my path. So if I just run this part and I load it, and I don't know how fast it will go, but basically I'm loading a save file with the species distribution, and it's going to be a little bit slow, so I will skip a lot of these things. But basically I'm loading a save file. Next thing that I have to do is just to build a table with 4 columns: the species, X, Y, data, and response. And with that, I'm basically playing with data, deleting columns and adding columns and so on and so forth. And finally, when I have it, I will show you. Well, it's taking a lot. Okay, so later on, I'm going to stop it, right? If you don't mind, just to show you as much code as I can in live. Cool. Okay. Yes. Interrupt the session. Okay. So then, what I have to do is load the variables into our format, into a stack format. Again, here is how to do it in code. Basically, you just list all files with the final extension, and then I put it on a pile on a stack, and then I plot all of them. All this is done. So first thing, if you get lost until here, sorry, I have it down here. So here you have the loading, the step that I made it. Next thing, and I'm sorry trying to go as slow as possible. So I need to format my biomode, and I have to tell sort of parameters, just like where are the present species, where are the X and Y coordinates, where are the characters, so on and so forth. I have to set up the biomode characteristics. Okay, I have it finally back the program with me, and I have to configure the model parameters. Just to show you what are the type of parameters. Let me see here if I can plot this one only. So my parameters will be, okay, it's going slow again. Sorry. So this is the type of parameters that I can put. I just can modify the type of parameters, the type of models that I'm running, the type of iteration. Okay, it frees. This is great to be live. To show, let me go to the different RStudio just to show you the script, and I will go back there. What I'm showing you is, sorry again, so I'm going back here. So you can modify all the parameters that you want. One important thing, you're going to have a problem for sure. I don't know why this never works. Maxen is making weird things with R. So if you have an error, you will need to download from here the maxen.jar and put it in the working directory. So once that is done, what you have to do is run the maxen model. I can tell here, I try to comment the script as much as possible. So you can declare here as many models that you want. In this case, I'm going to just run maxen, tell the option files, tell the number of runs that you do it, split, and I've tried to send you all the information that I can. And then finally, well, here you have another step. So in case you want to load it, and then I'm going to run the ensembles. So basically, again, is commented as much as possible. So I'll tell what I'm going to do, what is the metrics that I'm going to use, for example. Again, there's a lot of bio bibliography around that. I'm going to use true scale statistics. But again, there's a lot of things around here. Later on, I will project my model to the present, to the territory. If I have future data modeling, I will be able to project to the future. And then finally, I can study the results. So let me see if I can go back. Otherwise, I have it in R. I have it ready in R if it's in ArcGIS if it's a problem.
There is a question for you about Selena. She's asking that if it is possible to model multiple species at the same time.
Yes, of course. This is normally what we do. Just working with one species is just more for demonstration, but normally we just run hundreds of species. Hundreds, yeah. But we run 20, 30 species. But as much species and as much model, you need a more powerful computer. Just to benchmarking, I have a pretty decent computer with 32 gigs of RAM and a pretty good processor, and it's taking like half an hour just to do the full process. If you go for real with everything, we can talk about a day of processing in a powerful workstation. But yeah, this is something normal. So, I mean, the script is more or less trying to tell you everything, but I'm more interested in showing you the results. So if I go back to the presentation, sorry, I'll go back here. So once I do the model, I can have a lot of stats, and I'll show you the stats if I can. Sorry, not this one. Here. Okay, so once I run the model, I have 100 of stats, and I don't want you to lose too much. But basically, I can see the sensitivity and specificity of every model. So if I cut on the 90% of sensitivity, I can have the model. Just to go faster, sorry, I can see the variable contribution, and I can find that the June June NDVI is the most contributing. The slope is also contributing, and so on and so forth. We can see all the variable response curves. We can see the map results. So if I run all models, I will have this. Of course, this is all the possibilities from 0 to 1 according to your TSS. But if I do ensemble, I cut by 90%, I will get this. If I run more models, I will running with 5 models. Oops, sorry. I will have this on the right side. It seems really similar, but it has small differences. And of course, this is just one touch. If you want to go to enter in this really in detail, I just recommend just these 2 books. The one on the left is the popes of the disciplines, the more mathematical, the more practical. The one on the right is more hands-on with application with R. Finally, all these things can be put in R, and I can show in ArcGIS, and I can show you the model. I can show you the 5 models, and I can show you all together. And it's not loading. Great. Okay. And just to see the small differences, if I just zoom somewhere. So green is where both models just agree. Red is where my maximum model works, and blue is where the 5 models. So you can see the pattern is correct, but the difference are between 1 and 2. And I think is that for the moment. I mean, I know this is just too quick. I know that YouTube is not the best place for explaining R, but it's just, as I told you, just a little bit of open the appetite for that. Thank you very much, and if I will be here for any question.
Thank you very much, Isaac. We spend a lot of afternoons and days and months and years discussing about these things, how it works or not in a museum and beyond. And it's an amazing job. It's an amazing work that you can do working with these modeling tools that allow us, as I explained, to put in common our occurrence data with our predictors to get our spatial predictions for getting finally maps. So when we started talking about the botanist going to the field, we get maps. So after this whole development of occurrence data, training, classifications, predictors, and modeling approaches, we get at the end maps, as Isaac explained. And that's a very important part that we have to understand, to conceptualize when talking about the habitat mapping. So when modeling, we can only model using environmental predictors, abiotic limiting factors. So we will get information about the potential distribution. Let's call potential distribution. We are talking about communities, not the species, but the concept Isaac explained is the same, that when talking with ecological niche, that geographical distributions, we are talking about habitat distribution modeling instead of species distribution modeling, but it's similar. When remote sensing arrives to the equation, we make some kind of detailed analysis on in which locations, as Isaac explained, as these habitats occur. And when we put in common different the outputs for different habitats, we reduce the commission omission errors, and we get something related to the real distribution of the vegetation types in a space using the individual predictions. That's very well explained in a paper that we had that we published a couple of years ago, talking about this concept of the area of occupancy of habitat types with remote sensing. As I explained, it's something similar to the BAM diagrams of the species distribution modeling community manages, and maybe some of you knows well, and on which we reduce the potential distribution towards realized distributions of the species, and in this case of the habitats. So when we include remote sensing in this community modeling approach, we go through the potential distribution, as you can see in the upper right part of the image, to realize distributions of the different habitat types. That's what we call potential, local, and realized area of occupancy. So I am not going to go into detail because we have no time, but you can go read the paper and understand this a little bit better. Of course, the area occupied decreases as soon as we introduce better predictors and we put in common the individual prediction of different habitat types. So in terms of maps, that is the easiest way to understand this. What do we get? So what we get is the information, continuous information for the whole study area from which we collected training data, from which we collected predictor layers, the continuous distribution, the continuous probabilistic distribution of each of the habitat types at the EUNIS level, I remember, that we collected with our training data. If we put a threshold on that continuous probability, we can get finally something that is quite similar to the maps that we create with photo interpretation. I don't want to say it's better, it's worse. It's another way of producing the maps that will give us a similar information in a space that we can photo interpret. Then we will validate all this to see how good has been our work. So as Isaac explained, when we model only one habitat, we can get what we call the local area of occupancy, the local area of occupancy. But when we have multiple predictions, we can create algorithms that combines the dominance of each habitat type, the uncertainty of the individual predictions, taking into account complex statistical issues like the prevalence of the training data and so on. We can spend 1 week talking about this, but just believe on that we can handle, we can manage all this information for getting finally continuous maps for the whole territory on which we optimize the distribution of each habitat types in terms of the dominance of each one and the uncertainty of each individual prediction. And at the end, we have in a GIS something similar to a vegetation map on which we have landscape patches with the distribution of the dominant habitat types within them. For example, we can get a patch of forest habitat or forest distribution with the distribution of the different habitat types that are forest and are within that patch, maybe forest isolated patch within a matrix of shrublands or whatever. So at the end, the result is similar to the one that we get with typical photo interpretation analysis, but each pixel can be tracked in terms of the suitability of the habitat type that dominates and which predictor variables allow that habitat types to dominate, tracking the statistical analysis that we have done, as Isaac explained very well, in R or in any other environment. So at the end, we get these cool maps like we have, for example, in the project of Turkey. I show it because it's big, quite large, and we have the distribution of the different habitat types. But, and well, of course, we can publish papers with that, but we need to validate. We need to get independent information from the botanists, from the same ones or the others, and put on the table the information and see how our confusion matrices are good or are not good. Of course, we can put again our individual maps, our predictions of habitat distribution, we can put in common with the original maps that we use for training data or other maps that we kept for validation to see the agreement. For example, we can have the core inland cover, we can have the forestry map of each country, and we can check whether the information that we have at the patch level in these maps agrees or not with information that we have predicted with our mapping approaches. We can use different maps, the typologies will not be the same. As Borja explained, we will have the paths to change the typologies, and we can play with that to make a validation. So the individual predictions, the combined predictions are probability distributions, probability maps, that we can convert using thresholds to maps, and we need to validate with independent information, as Gonzalo from the AH team will explain you with the last hands-on. So everything is yours, Gonzalo, to show some tips of this GIS processing approach.
Okay, can you hear me?
Yeah.
Yeah. Okay. Okay, thank you, Jose. Hi, everybody. My name is Gonzalo, and I'm going to make a practical exercise about habitat mapping and validation for probability classification raster. In the step 1, we load the probability classification raster in the R map. Sorry. Okay, we can see that the values go from 0 for surfaces with low probability to 1 in surfaces with the high probability. In properties, we go to symbology and classify to assign 2 classes with a break value in 0.6. Select. If you compare with the original classification raster, you can see that the occupation surface of the habitat is being reduced. To work with values of absent and present in ArcGIS tools reclassify, we select the probability raster as input, the value file as raw class, and we assign an output of 1 for values for 0.6 to 1 and an output of 0 for the rest. Finally, we select the output raster always in TIFF format. Okay, now in step 2, we are going to apply a low pass filter to the raster obtained in the previous step. The effect is that the height and low values within each neighborhood will be averaged out, reducing the extreme values data. To do it, we use the tool filter. Then we select the absent and present raster as input and the type of filter, in this case, tape low. And finally, we select the output raster. Okay, the result is a new raster with continuous values from 0 to 1. We repeat the previous steps for a better understanding using a new break value of 0.8. Symbology, classified, 2 classes, classify again, and 0.8. If we compare again with the last classification raster, you can see that the occupation is reduced again. Again, to can work with values of absent and present, we use the reclassify tool. Sorry. Okay, in step 3, we get the confusion matrix for the final classification. For you test it as the ground truth data, we will use the training points original. Okay, first, we create a new field in the point shape. We select a new name and the type of source integer. Load in the ArcMap, open attributes table, select, add field. Okay, we assign value 1 to every row with value at 2.5x in EUNIS 4 and 0 for the rest, using the select by attributes option in the attribute table. Okay, select by attribute. EUNIS 4. We get unique values and select. And now we go to the calculator and value 1. Okay, now we are going to use the extract multi-values to point tool to assign each one of the set points the value of the final classification raster. Okay. Final classification. Okay, you need to delete the shape and load it again. In this case, it's not necessary. Okay, next, we use the tool frequency that creates a new table containing our field values and the number of occurrence of each one. We can use the save point as input. Select the name. Select the true data and the final classification. At last, we use the pivot table tool to create a new table from the input frequencies by reducing the redundancy in records and fitting one-to-many relationship. With this table, we can check how many points of ground truth data are currently classified in the final map. First, we select the classification, the pivot file, the through, and the value, the frequency. In the example, we get 32 currently identified points out of 84. With this data, you can now calculate the overall accuracy and the commission and omission errors. Now it's your turn to try a new brick values to get a better classification and try with other habitats and have the final mosaic map. Thank you very much and see you soon.
Well, thank you very much, Gonzalo. And we go to the final part of the session. And I thank you very much for this presentation that together with the one from Borja, Ana, Isaac, and now Gonzalo, wanted to show you that creating the maps is not just clicking something somewhere and getting the information. You have many steps in between that sometimes, I don't want to say are boring, but are serious steps that we have to think about, have a deep knowledge on what are we talking about. So I share my screen again with the presentation. Okay, so just to make some 5 minutes remark highlighting that sometimes, even though we do everything correct and we download the images and correct everything perfect, we have a classification procedure, good training data, our predictors perfectly organized it for running our models. Sometimes the complexity of landscapes allow us to improve our capabilities by changing the predictors, going to the field with more expert knowledge and getting more data, for reducing the uncertainty of the prediction because of the uncertainty of the capabilities of our predictors, mainly related to the capabilities of the spectral, spatial, and temporal resolution of satellite imagery. So this is an example of the colleagues from the coastal, that work in the coastal areas here at EH Cantabria, with two classifications with Landsat here and Sentinel here. We can see that improving the resolution of Sentinel improve the predictions in these coastal environments. This is an example that we have been working also with wetlands here in Cantabria, that we tried mapping with Landsat, we tried mapping with Sentinel only, Landsat and Sentinel, both with temporal resolution for including the vegetation phenology. And finally, we create a function, and we made function analysis with Sentinel, with very high resolution satellite from Deimos, also with LiDAR topography, getting finally more suitable, more reliable predictions. We are working now with the grasslands, also in the Cantabria region, including also the Alice case study, where we go a little bit more far away, and we have gone to the field, identified the different typologies, and we have been playing with all the capabilities of the medium resolution, Landsat, Sentinel, and MODIS, and we finally concluded that we need to go to the field and work with the hyperspectral capabilities. We have here at the EH Cantabria an hyperspectral lab that Anna and other colleagues manage and use the different tools that we have, creating a spectral library from different vegetation types and vegetation communities with the capabilities of this lab, with the file spec 4 that have very large capabilities of assessing the reflectance at a very detailed resolution of the wavelengths. So we work with the different species, with the different communities, but also with phenology, going to the field to take the spectral signatures, the hyperspectral signatures of the different communities, going also to the lab to calibrate that observations to be sure that we have been talking about, or finally being able to identify which communities can be differentiated with other communities, and how these differentiations using approaches of spectral angle mapper can be seen, which these of kind differences can be seen with the medium resolution typical satellite images as Sentinel-2 and Landsat. With this information, we make like trade-offs between the classification procedures that we have been explaining now with the modeling approaches using in situ data and the real capabilities of the spectral resolution of the satellites and our whole predictors for predicting that thing that we want to map. So we are not going only, with supervised classifications, but we are going into the high detail of the capabilities of remote sensing and how and when should we use for creating that predictions properly. So everything is it's some kind of a feedback with the occurrence data, with the predictor variables using remote sensing for creating the community level modeling approaches for creating our maps that will be validated and each step improve the capabilities for prediction. We don't stop. I want to spend just a couple of minutes. We don't stop in mapping patterns, but we want to map processes, the dynamic of the system, and the functioning of the system, and in brief, to mapping the state of conservation of the habitat types. We have been making an effort with one colleague that is working on this, trying to understand all the guidelines that the ministry is putting on the table to doing a monitoring of the habitat types. We are studying quite deeply all the recommendations of the ministry for creating finally our final pool of indicators that can be modeled using remote sensing for the different habitat types, for grasslands and forests. We are in wetlands. We have been already done this kind of analysis, and finally using the different capabilities of the medium resolution satellite images and the very high resolution, and also the drones, LiDAR, hyperspectral radar, and so on. We create time series of satellite imagery using the capabilities of Copernicus and using our own developments in collaboration with David, one colleague from one company quite close to our work here at the Cantabria. And in such a way that our real information on the ground that we have from the botanists that I told you is not only talking about, it's not only about the presence or absence of a community, but also about the conservation status of that community can be tracked with the time series of satellite imagery, going not only to download the images, but to identify the problems of that images, clouds and shadows, that also smoothing the time series of information, or finally getting indicators that allow us to identify what happens and when some kind of changes and some kind of dynamics that allow us understanding what is happening with that patterns that we observe now, that we can track from the past, in the past, with the approaches of landscape dynamics that Thomas told us in the beginning. So just going to give you 5 minutes, I will go after hour, but 5 minutes, talking about all this information is not used only for mapping with no objective. Here in the ALICE project, we have the objective of understanding landscape dynamics for improving the functioning on landscapes towards a multifunctional, towards creating or helping creating multifunctional territories in the way of ecosystem service provision and supply was better through the development of blue and green infrastructure networks. But we can just track monitoring for reporting and of course creating management guidelines to improve the landscape. So we move towards the changing landscape to something more functional. That, for example, this example is talking about vegetation dynamics. We not only want to know where a landscape changed, but also why and how that change has affected the function, the ecosystem services, and how can we improve this through the development of time series of satellite imagery informing about indicators that give us information of that dynamics. So at the end, we can understand the whole process, afterwards focusing on the changes and on the processes that we are interested. This is an example of how forest dynamics controls that one of the main topics researched within the ALICE project, how landscape dynamics and specifically forest dynamics affect the hydrology of the water basins in terms of water quality, water quantity, flooding, and many other aspects related to the river functioning. So some dynamics and some patterns drive us towards good functioning and provision of ecosystem services, while others that we can identify now in a spatial explicit way need to be restored or improve the function of that system. So in terms of management, just to simplify, we can conserve, we have preserved that areas that work suitable in a suitable way, or we can restore other areas that are not working properly. As soon as we have the habitat maps, as soon as we have the distribution of the biodiversity patterns, and we have the information about landscape dynamics, we can know at each point if we have to work in the structure, function, in the distribution of that habitat, in the pressure that are altering that disturbing that habitats for making that restoration actions more effective. So we can disentangle, we can split that restoration actions in different indicators that will be the indicators of conservation status that we mapped previously for identifying the conservation status of each habitat type. So we know the patterns, we know the indicators that inform us about the conservation status, so we know where we have to work for improving that patterns. We can include everything in a chain process that we have well defined now for creating also a priority index that will inform us on how and where and when we have to work on that indicators of conservation status for improve the final pattern of our biodiversity, of our landscapes, that will improve the functioning of themselves. So just to show you an example of how to do this instead of going to the GIS, because as Gonzalo explained, there are many steps, changing the tools, opening the tools, and running the tools. This is a quick example of how to proceed. So we have everything that we explained before. We have the distribution of the habitat types. So we know where we have the habitat types. We know how that habitat types are distributed in terms of different indicators that we want to track the guidelines of the ministry, and we will add others that are not included in that guidelines, but we or the bibliography, the experts have used previously. We are collecting a very complete data set of indicators. So we have everything distributed in space and through time. So now we define management areas. We have some landscape features, as Thomas explained, on which we focus our analysis. In this example, is the Nature 2000, terrestrial Nature 2000 areas of Cantabria. The eastern part are included in the Alice project, but you have the whole picture, on which we can overlay the information of the distribution of our habitat types. Okay, so if we, as Gonzalo and Isaac explained, if we cut that distribution with a threshold, we can identify the areas, the local areas of occupancy, the current distribution of that habitat types. If we go in detail, so we can identify the areas on which the habitat types now is distributed. We can identify the areas on which the habitat types is distributed but in a bad conservation status because of different reasons. Structural, functional indicators will inform us on where do we have let's say the habitat well expressed and the habitat with low conservation status. And just to make it simple, we can identify for each, we can identify for each of the landscape patches, the management units, we can identify on which of them do we have our habitat well distributed, in which of them do we have the habitat in a bad conservation status. We can also identify how, for each of the habitat patches, how landscape evolved in time. Imagine, for example, that we have one area with a bad distribution of one habitat type, let's say Acidophilus beech forest, but we identify that in time, in that landscape patch, forests are expanding. So we know currently that the ecological status of that habitat type is not good in that location, but we know because of the landscape dynamics, and this may help to understand the question that was stated before. We know that the landscape dynamics are evolving towards a forestry area in the future in that location. So maybe the habitat is not well preserved now, but maybe in the future, if forests evolve with no disturbances, that habitat will improve in that location. So we can map that. We can also make landscape structure analysis and know the connectivity, as we will explain later, the fragmentation of that habitats in any of the conservation status that we want across space. We can identify pressures like fire risk if we have in that patches, the existence of alien species. We can identify things about primary production with time series, as I explained you, of NDVI or other indicators. And finally, we can use some kind of systematic conservation planning approaches or multi-criteria analysis or whatever to identify the areas that are that we can prioritize for conservation, that we can prioritize for management in the different options that we can manage the territory. Of course, we can include simulations in the future and the climate change for getting information on how this landscape will evolve and how that can affect, how that can stress our vegetation patterns to take decisions in terms of climate change and in terms of improving the functioning of our landscapes, of our biodiversity patterns into the future by having differences between now and future and include in our decisions. That's what we did in this big project in Turkey. Finally defining the Nature 2000 areas most suitable that would fulfill all the criteria that I have explained you for defining really functional Nature 2000 areas. And of course, that's what we want to do, as Thomas explained in the beginning with Alice, going from satellite data to collaborative management by taking decisions in the base of all that big sort of information that we have developed. And just for finishing, if we put Alice into practice, and in the GIS again, I'm going to demonstrate because I don't want to use more time that we have scheduled, but we can go again to our training data set, to our study area. We can go to our a small subset of our study area in Alice. And here we know we already have information about the landscape. We have information on how this landscape evolved in time. We have information from the past, information from now, information from the future. So the different land cover patches that we have in the territory that here in Alice is a mixture of, as Thomas explained, of LPIS databases and some kind of topographical constraints. We have the different land cover patches. I'm going to put it here. That in such a way that we can get from each patch the dynamics of the landscape, as Gonzalo explained, we can get the distribution, the maximum probability of distribution of the different habitat types for each patch. So in such a way that we can run afterwards analysis on how that landscape dynamics is related to the biodiversity patterns. That is something that we are now currently working with the Alice project. So we have given you information about the all case studies of Alice. We have a detailed explanation of each step and also the script, the R scripts that somebody asked in the folders that we gave you for putting Alice into practice by yourself, running examples. And of course, our emails, our contact is there for helping you for more discussions and for going a little bit more into how habitat maps can be linked to landscape dynamics for improving the functioning of our landscapes and finally our quality of life. And thank you very much.